At 13 minutes past 8 in the morning, Siberian time, on the 17th of August 2009, a 920-ton steel rotor came out of the floor. Not sideways, not slowly. Upward, still spinning at 142 revolutions per minute, through the deck of the machine hall of the largest power station in Russia. Behind it came the Yenisei River at 20 times atmospheric pressure through a hole the size of a house. 75 people were killed. Most were not operators at a console. They were welders, electricians, and fitters working in the galleries underneath the turbine floor, rooms that filled with water in under a minute. There was no explosion. Nothing detonated, nothing burned. A machine simply came apart, and the reservoir it had been holding back for 30 years walked in through the gap. And here is the part that makes this file worth opening. That machine had been announcing what it was about to do for 4 months, in numbers, written down, every day, on paper that people signed. Start with the object itself because the scale is doing a lot of work in this story. The Sayano-Shushenskaya hydroelectric station sits on the Yenisei, in the Republic of Khakassia, deep in southern Siberia. Its dam is an arch-gravity structure roughly 245 meters high, one of the tallest in the world, holding back a reservoir over 300 kilometers long. Inside the machine hall at the toe of that dam sit 10 turbines, 6,400 megawatts of installed capacity. That made it the largest power station in Russia and the 6th largest hydroelectric plant on Earth by average output. Its electricity ran the aluminum smelters of southern Siberia, which is to say it ran the regional economy. Each unit is a Francis turbine, a steel runner nearly 7 meters across, sitting at the bottom of a shaft, with water arriving around it through a spiral case and leaving downwards through a draft tube. The rotating assembly, runner, shaft, and generator rotor, weighs 920 tons. That is roughly 2 fully loaded jumbo jets, spinning 2.5 times a second, 1 floor below where people walk. And the only thing separating that spinning mass from the full pressure of the reservoir is a steel lid called the head cover. It is bolted down. Remember that word. Now the question that decides everything that follows. A turbine this size does not like being adjusted. Each machine has a chart from the manufacturer showing which power outputs are safe at a given water level. On the 17th of August, with the reservoir at 212 meters, that chart for Unit 2 looked like this. 0 to 265 megawatts allowed. 570 to 640 megawatts, the recommended working band. Above 640, forbidden. And in between, from 265 to 570 megawatts, a band marked not recommended because in that range the water flow through the runner becomes unstable. It pulses, it hammers. The whole machine shakes. Look at that chart again and you see the trap. The not recommended band sits directly between idle and full power. There is no way to bring the unit up or down without driving it straight through the zone the manufacturer told you to avoid. Cross it quickly and stay in the working band, and that is survivable. But hydro plants are not run like that. Hydro is the fastest thing on any grid, so hydro is what the grid uses to absorb everyone else's mistakes. When demand moved, Sayano-Shushenskaya moved, and every time it moved, Unit 2 went through the bad band. Unit 2 was installed in 1979. Its manufacturer gave the design a service life of 30 years. On the morning it failed, it was 29 years and 10 months old. It had never been an easy machine. Between 1980 and 83, it had seal problems, shaft vibration, and bearing trouble. In 2000, it was stripped down for a full reconditioning, and the engineers found what a Francis runner looks like after 2 decades of unstable flow. Cavitation pits up to 12 millimeters deep and cracks up to 130 millimeters long in the blades. They welded them up. 5 years later, they found more and welded those too. Cavitation, for the record, is not corrosion. When water accelerates around a blade, the local pressure can drop low enough for it to boil at ambient temperature. Vapor bubbles form, drift into higher pressure, and collapse. Each collapse is a tiny implosion against the steel. Do it a few billion times and you get craters. Every one of those repairs was a symptom of the same thing, a machine spending too much of its life in the band it was told to avoid. And every weld changed, very slightly, how the runner was balanced. In January 2009, Unit 2 went in for its scheduled modernization. It came out in March with new electro-hydraulic governor equipment, the system that controls how fast the machine responds to a change in demand, and with fresh weld repairs on the runner blades. What it did not come out with was a properly rebalanced runner. The consequence appeared immediately in the logs: 150 micrometers of runout at the main bearing at full load. Then it began to climb. Between the 21st of April and the 17th of August, the vibration measured at that bearing increased by a factor of 4. The manufacturer's maximum acceptable value was 160 micrometers. By early July, Unit 2 was past it. For long stretches of that summer, it ran above 600 micrometers, while every other unit in the hall sat below 200. You would expect that a number 4 times the limit triggers something: an alarm, a trip, an automatic shutdown. It did not. The vibration sensors on Unit 2 fed a monitoring system, and a monitoring system is a diary, not a break. Every day the readings were taken, recorded, and filed. The machine was screaming in writing into a folder. Which brings us to the night of the 16th of August. At 20 past 1 in the morning, 600 kilometers away, a fire broke out at the Bratsk hydroelectric station. It did not injure anyone. What it destroyed was communications, including the regional link that let the grid dispatcher control power output automatically across Siberia. With Bratsk out of the loop, Sayano-Shushenskaya took over the job of balancing the grid. And within the station, one machine had to be nominated to lead: the unit whose output would be adjusted first and hardest, second by second, to hold the frequency steady. They chose Unit 2, not out of negligence, out of logic. It had just come back from modernization with the newest governor in the building. On paper, it was the most responsive machine they had. So for the next 7 hours, the most damaged turbine in the hall was handed the grid swings. 600 megawatts, down to 100, back to 600, down to 200, up again. The plant's total output moved between 2,800 and 4,400 megawatts across the night. Every one of those transitions dragged Unit 2 through the not recommended band, and every pass through it loaded the bolts under the head cover one more time. At 12 minutes past 8, the automatic regulator began pulling Unit 2's output down again. The machine was at 475 megawatts. The bearing vibration reading was 840 micrometers, more than 5 times the manufacturer's limit, and more than 4 times any other turbine in the building. 1 minute later, the head cover let go. It was held down by studs. Investigators later recovered and examined 49 of them. 41 had fatigue cracks. On 8 of those, the crack had eaten through more than 90% of the cross-section, meaning that for those bolts, roughly a tenth of the metal was still doing the job of holding a reservoir out of a building. Across the set, fatigue had consumed an average of 65% of each bolt, and at least 6 studs had no nut on them at all. Not sheared off, never fitted. Some showed no trace of a nut ever having been tightened against them. What happens next takes about 20 seconds. With the fastenings gone, the pressure under the head cover did exactly what physics requires. 200 meters of waterhead, about 20 bar, lifted the cover, the shaft, the runner, and the 920-ton rotor vertically out of the seat, still turning. The rotor rose through the generator floor, tore itself apart against the structure, and came down across the hall. Behind it, the spiral case was now an open pipe pointing at the ceiling. 256 cubic meters of water per second entered the machine hall. The galleries below the turbine floor, where most of the maintenance crews were working, flooded almost immediately. 9 of the 10 units were running at that moment. As water reached them, they short-circuited and destroyed themselves in sequence. Units 7 and 9 were wrecked outright. Transformers 1 and 2 exploded. Part of the machine hall roof collapsed into the water. The station went from 4,400 megawatts to nothing, which created the problem that could have turned a disaster into a catastrophe. The gates that shut off water to the turbines are closed by the station's own power, and the station no longer had any. The reservoir was now draining, uncontrolled, through a hole in a building at the base of a 245-meter dam. The only way to stop it was to close 10 intake gates by hand. Each weighs 150 tons. The controls are on the crest of the dam, hundreds of steps above the flooded hall, and they had to be driven with manual hydraulic jacks. A group of workers climbed up and did it, 10 gates by hand with no power, while the building below them filled with water, and they had no way of knowing who was still alive inside it. They finished in about 25 minutes, close to the fastest that operation can physically be done. Rescue teams worked in the flooded galleries for days. 2 men were pulled out alive on the Monday from air pockets inside the drowned structure. One had been carried upward by the flood until he reached the ceiling, where he caught hold of ventilation equipment and held on. As late as the night of the 18th, divers reported hearing knocking from below the waterline. 75 people did not come out. The investigation by Rostekhnadzor, Russia's industrial safety regulator, was published on the 3rd of October 2009. Its conclusion was not that a bolt broke. Its conclusion was that the bolts had been broken for a long time and that the organization had a complete written record of the process that was breaking them. Excessive vibration, tolerated. Repairs signed off without rebalancing. Inspection intervals that never once asked what 4 months of rising numbers meant. 7 people were eventually charged. The station's former director, Nikolai Novolko, its former chief engineer, Andrei Mitrofanov, and 2 former deputy chief engineers, Gennady Nikitenko and Yevgeny Shivarly, received prison sentences of between 5.5 and 6 years. Downstream, at least 40 tons of transformer oil escaped into the Yenisei, spreading an 80-kilometer slick that killed around 400 tons of farmed trout before it was contained. Rebuilding the station took 5 years. The last works were completed on the 11th of November 2014. The replacement turbines have a 40-year design life, a wider stable operating range, and something Unit 2 never had: vibration monitoring wired directly into the protection system with the authority to stop the machine on its own. That is the lesson, and it is a narrower one than it first appears. Nobody at Sayano-Shushenskaya was missing information. The vibration of Unit 2 was measured, logged, and reported for 4 months as it climbed past the manufacturer's limit and kept going. The failure was not that the machine gave no warning. It was that the warning had nowhere to go except a filing cabinet. A measurement that cannot stop a machine is not a safety system. It is a record of how the accident happened, written in advance. If you want to see the same principle fail in a completely different material, watch the Hyatt Regency file, where a single change to a hangar detail doubled a load that nobody recalculated. Different country, different century, different physics. The same gap between what was known and what was acted on. The engineering files. Subscribe, and we will keep opening them.